Hello everybody, we're back again. We are going to attempt today to do another 20B engine assembly. This is a video more at the customer's request. As we've told you guys before, we do offer video services for anyone who wants to get their assembly filmed. So very briefly, we're going to go over some of the modifications that we're doing to this engine. And we're going to take you through sort of the disassembled individual components, and then we're going to film the entire assembly. The difference between this motor and the last three-rotor that we put up on YouTube really is only going to be the fact that this is a dowel pin engine. So for those of you who follow our YouTube channel, you'll see that not only have we done a three-rotor Bridgeport engine buildup, which is exactly what this one is again, but we've done a studded 13B. So similar to a studded motor, we're adding the extra dowel pins in this three-rotor for strength, but we're not using through studs or 12.7mm studs like we did in the stud video. We are actually going to be using a dowel pin method that we've been using even longer than we've been doing and offering studding. And we'll talk a little bit more about the reason we do it the way we do as we're assembling a little bit later on in the video. For the time being, we'll just recap the build sheet. This is Colin Harris's 20B build. This is a A-series engine, or B-series, which is one of the reasons why we're adding the extra dowel pins, is because the A-B series as compared to the C and the D series engines are not nearly as strong. There is more casting material around the upper dowel pin area on the later engines, the C and the D series. And in this particular case, he's running a very big turbo. We don't know how much boost yet, but to be ultra safe for his end user goal of potentially race gas and 20, 30 pounds of boost, we are going to build the engine stronger than we think it will need to be built, simply for the rule of thumb, overbuild and underdrive, and the engine should last. So we are going to add the extra pins. We are also going to put in, for strength, the early turbo 2 rotors, the 87-88 low compression, heavy duty turbo rotors. A very, very strong rotor, almost indestructible. We're going to do lightning on the rotors so we can take away some of the negative aspect of putting in that rotor, which is extra weight. So we want to kiss some of that extra weight goodbye. And once we lighten the rotors, we're going to have them clearance and tip clearance, which is what's called our race clearancing. We've demonstrated a lot of these rotor mods in previous videos, but I'll just wrap them up and say that the combustion chamber clearancing is another thing we're doing on these rotors. We're putting in new FD bearings to match up with the 20V shaft, because the early 87-88 turbo rotor bearings won't be as much of a clearance as we want. They won't be, there won't be enough clearance if we use those bearings. So we are going to upgrade to the FD bearings. And the dowel pinning, as we discussed, half Bridgeport, lapped secondary faces, and all the oil modifications and the high pressure oil regulator. If I missed anything, we'll catch up with it later. We'll take you through as we build, and see you then. So as we were talking in the intro about the dowel pin mod that we're going to do this engine, we've already got our center housing mounted up on the engine stand, and this will be an easy way to demonstrate what's happening with the extra pins and where they go. So Colin has requested that we do the dowel pinning because this is an A-series block. It's either an A or a B. It is not a C or a D. And for those of you who don't know the difference, that is the main thing is the thickness of this dowel pin area right here. And on a D series or a C series, you'll see it's much wider and there's much more meat on this plate and the back and the front. Because it's an A or a B, we're going to add our reinforcement pins in the combustion chamber area only. That's the only place that's actually necessary. So these pins are designed to go in these counter bores, which our machine shop's done for us. And what will end up happening is this being the 13B side, actually the back half will have the longer pins, and we will have tension bolts actually going through these pins and into their respected threaded bores. And that's going to happen on 3 places on the 2-rotor side of the motor. And it's going to happen in the same 3 places on the front side of the motor, the 3-rotor side. And that's when we use the short pins and going through the dowel pin, again, into the associated bore. And we're not going to turn this around and show you that because it's basically a mirror image of what you see here. But I'll just show you, you guys the actual pins. So again, we're using the factory 6 alignment pins, 2 of which, as we'll discuss when we're building the engine, have the cutback on them. So these 2 here, probably can't see it in the camera, but these are actually cut down and actually a narrower pin on this last inch. These are for the front. And these 4 are just like a regular 13B engine. Those are for the back half. Okay, so we are going to be using the factory alignment pins, and we're going to be using these 6 additional pins in the combustion areas in their respective bores, as we showed you. Further to the pinning, you probably noticed on that center plate and also on these front and rear housings when we're talking about the secondary port. We have our large ported main intake port with our half bridge port. And that's, again, only on the secondary ports. We did only a street port on the primary ports. Another thing you'll probably notice too is that all the primary port faces, including the other side of the thick housing, we actually chose not to lap because Collins plates were in immaculate condition. And we chose to leave the lapping alone on the plates, so we did very little work to them. However, whenever we do Bridgeport work and we have more room for getting little burrs or sharp edges, what we like to do is we like to lap this surface afterwards and make sure that this area around the port and around the bridge actually gets lapped. So you'll see that there's a lapped finish on the secondary port faces and not on the primary port faces. These are very, very big intake ports. Not sure if the camera is going to demonstrate this well or not, but that is what we get for the runner size on all these 20B secondary ports. And that's the size of the port, the main port on the secondary port on the motor side, and that is the bridge port. So this thing is going to flow like mad. Last we have the exhaust ports. Essentially, we're reusing these very good condition rotor housings. The chrome on these are in immaculate condition, so we told Colin to go ahead and it'd be safe to reuse these housings. Again, I don't know if you can zoom in on the port there, but we do our typical large D-shaped exhaust port, and that's what you get for the other side, if that demonstrates anything at all. And that's really all there is to show on these particular housings. We'll move on in a minute to show you the gears and the oil modification work we've done and the rotors.
Okay, you're good.
So the oil modifications, very simply, we have installed the Racing Beat Mazda Race high pressure oil regulator in the back plate already. We've done some of the enlarging of the galleries here on the rear plate, also in this hole, which is going to be hard for you guys to see, and then also the gallery that actually feeds the rear stationary gear, and then enlarged the hole in the stationary gear itself, match ported all that together, and same with the front, same with the middle. So you have a larger match ported hole in the gear through the bearing, which then in turn matches this gallery here that flows oil to the front bearing. And we've also gone ahead and enlarged the passageways to that gear gallery, away from the oil pump and down through this turbo feed gallery. We've also opened up the gallery that flows the oil through the front cover and out the front cover to the rest of the oil system. And we've also ported out and enlarged the galleries, the discharge galleries from the oil pump and also in the suction side of the oil pump. So basically all the oil modification work has been done within all 3 housings. And that's about it for that. Last thing, we have chosen to use this stock crankshaft exactly the way it came out of the motor. Again, this is a very low mileage, clean engine. Saw no need to polish up the crankshaft. Measured everything, measured out perfect. So we're going to leave the crankshaft in stock form. We haven't done anything with it. Rotors, we've switched from the standard 20B rotors to the early 8.5 to 1, low compression, very strong, what we call our heavy duty upgrade rotors. And for those of you who have not seen the work that goes into the rotors we offer, we'll start with the obvious. This rotor has been lightened on both sides. And we have also clearanced the faces, done the extra clearance work around the tips of each rotor. And lastly, we've done the combustion chamber clearancing, which means all the way around this pocket we've removed material sort of on a linear basis, so it gradually steps down to its highest clearance in the middle and then blends right about where you see the line end there with the factory dimensions of the rotor. Very important for high boost, high horsepower applications where the crankshaft might flex or deflect and allow the rotor to hit the chrome on the rotor housing. So these rotors have already had new bearings installed. We're just in the middle of putting in the new oil seals, and then we're going to fit the corner seals and the side seals. And last, when we assemble the engine, we're going to use our own rotaryengine.com 2mm race apex seals. These are our treated seals, along with new springs, and we'll see you when we get to that point. So further to the bridge porting we just showed you guys a minute ago, one of the things that we have to do with a bridge that goes very close to the water jacket seal to get maximum flow and port timing opening is we actually notch the rotor housing here, which basically matches the little half bridge that's on the secondary ports only. So you'll see there's no notch on this side, but there is a notch on all three housings, which means not only do these rotor housings have to be labeled front, center, and rear for the sake of the front housing actually has 4 large 12mm tension bolt holes drilled into it, and the other ones, the rear, center and rear, only have 2. That's one reason they have to be designated front, center, and rear. The other reason, again, is because we have put these notches in. Not only will the notch be on the opposite side of the housing, front compared to back and so on, so they have to be specifically matched, but they're also further matched exactly to the actual port. So for example, this is the front housing, and this is the front plate with the bridge port work. So by the time these two go together, that notch and that secondary bridge are going to match together, and they're going to be in the exact position because those two pieces have been matched to go together. So another reason why we have to keep these organized and designated, and just a little bit more information for you guys on the procedure that we use to maximize flow on the secondary bridge. One. Okay, on with the assembly of Mr. Colin Harris's 3-rotor engine. Picking up where we left off last, we were talking about some of the reasons to do dowel pinning as compared to studding. So a lot of people who are aware of what the reason is for putting studs or dowels in a motor. If you've seen our past videos, we talk about it a lot. For those of you who are not familiar, just to recap, we're trying to gain extra strength, mainly in the combustion area where the cylinder pressures are the highest. And in the case of a 3-rotor engine, we do not want to use studs like we do in the 2-rotor. Especially through studs that have, and race studs that have minimal 2 to 3 thou clearance, which is about the same clearance and tightness as a factory alignment pin in its factory bore. It's no more than, or no less than 3/1000ths of an inch. And the reason you don't want that tight clearance is because on 3-rotor engines, the crankshaft is a 2-piece crank. and it's not accurate in high RPM application, and after lots of heat cycling of the engine, warming up, cooling down for regular road car use. It's not an accurate line bore in the engine. They don't have the luxury, even at Mazda, to be able to design a two-piece crankshaft that can maintain a very accurate line bore. So what they do in the case of 20Bs is on the front section of the motor, it's deliberately left loose. And what I mean by that is, so right here as we're doing the center rotor housing in this engine, these are no different than regular 13B dowels. They are symmetrical end to end. And these are going to go in just like they normally would in a 13B. They're going to get countersunk the same depth. The center housing is going to sit the same way. And the back half of the motor is going to be just like doing a 13B, where we could use either rigid studs or rigid dowels. So what you'll see is on the front section of these 20B dowels, they're very, very close in their overall outside diameter here as they are here, but they're stepped down just a little bit, about 0.06 of an inch. So what we've done on our dowel pin method is on the back, just like these ones that don't have the cutback, these alignment dowels, these dowel pins are actually going to be the same sort of clearance as these and the same size end for end. What we're going to do on the front section, which Mazda keeps deliberately loose by way of using these sloppy pins, is we've done the exact same thing with our dowel pins. We've actually got those cut down on the ends here. So when they countersink in, we are also going to have free movement of that front section of the engine, just like it was from the factory. So that when we start torquing things down and we find that the line bore where it wants to be, we're going to have some float built in. And that's one of the bigger reasons why we're not using through studs or rigid dowel pins or long studs like this on the back on the front. So we'll cover that again when we get there. For now, we got to get moving here and get this this engine together. So we're just going to continue to build this. What you're going to see is that from this point forward here, this engine assembly is almost identical to doing a two-rotor engine. It's virtually the same process. Everything's the same. The only thing that's going to be different is at the very end, right when we are about to put on the back housing, the rear end housing, we're going to slide the solid one-piece additional dowel pins in. And I don't know why we're struggling so much with this, but we shouldn't be. Got a spring here that doesn't want to go down. But we'll be putting those dowel pins in right before the back plate goes on, and then we will assemble the front section of the motor, and we'll show you again those dowel pins that have the extra cutback. And just got to finish this off first. So, thank you. By the way, we used to do and still have every capability and availability to our customers to offer dowel pinning as opposed to studding on 13B motors. We can do a 13B doweled engine, much like the back half of this motor, where all the parts are going to be the same long one-piece pins and so on. And we can do that. The reason why we don't sell a lot of dowel pin 13B engines is very simple, because 13B 13Bs that we build that need to be very strong, we would aim towards doing studding. And people say, well, you know, I thought they were both a rigid process, and you know, you don't have to have any player movement built in, which is true, you don't. But if you're going to go through the trouble, and we get all our stuff done on CNC, so each piece, each housing, rotor housing or end housing, all of them, whether it's 2-rotor, 3-rotor, all of them have to be done to each piece independently on the CNC. And if you're going to go through that kind of trouble to if you're going to go through that kind of trouble to make that happen, you might as well, instead of doing 3 holes or three dowel pins additional in the combustion area, we might as well, instead of just doing these 3 locations, do every single hole all the way around, which is exactly what we do when it comes to the studded motors. And you know, nothing beats, there's no downside to having extra pins. So we just choose to go ahead and do all the locations and use studs, which essentially means that every tension bolt now becomes a dowel pin, contact all the way around every hole. So again, instead of in just those locations, we do all 16 holes all the way around. And again, that can be done. I'm going to do real quick here. This is down. We're going to rotate this. Again, I don't know if anyone can see it in the on their monitor or not, if the camera is exposing it, and it's not important. We don't have to zoom in or anything to show this, but as we mentioned before, you may have noticed that the side of the housing, of the thick housing, facing up, that was exposed before we put the first rotor down, is a lap surface. And we did lap all the secondary port surfaces with the Bridgeport. The primaries, we actually chose to leave the way that they were, and they're not lapped, and they were in mint condition. Very little stepped wear, very little oil control ring wear, and absolutely as good as they can be. So we left them alone, and that will take away nothing from the build that this engine is going to be. Okay, so as soon as we get this next rotor housing in place, we're actually going to aim to slide the dowels, our additional dowels, in place. Let's just get this rotor housing on first, and then we'll move on to that part of the process. Incidentally, we went through great lengths in the 13B stud video that we put on YouTube to talk about the accuracy and the tolerances that there are when you're doing studding. And I'll just mention that with dowel pinning, there is equally the same amount of accuracy, and that's something that is just as important in a dowel pin motor, if not more important, than a studded motor, because you're doing it in a few extra places rather than all the way around. It's very important that everything fits properly and that everything's done to a very tight tolerance. So luckily we have that availability based on the competency level of the machine shop that we've been using for years, and they just keep getting better and better. So that's a good thing. Actually, before we put this in, let's go ahead and put those pins in now, Put the apex seals in after, once we know these are good and seated. One. And you see how I'm leaning into these slightly to get some weight on them, but did you see how beautifully those went down with just a little bit of my own weight pushing down on the ends of these dowels, and they literally slid in. I mean, I want to say better, tighter than the factory Mazda alignment pin. They were actually tighter than that, but beautifully smooth and accurate. And that's exactly what we were aiming to do, and that's exactly what we got back from the machine shop. Very happy with that. So you'll see that they're sticking up about the same amount that they were submerged. They were probably counterbored a little bit more into the thick iron for the sake of achieving a little bit more submersion in the plate where tension bolts are tugging on either side of that particular iron. So we went a little deeper on the center iron, but as you can see, the amount that these are sticking up here is exactly what we wanted, about a ½ inch. And if there are excessive cylinder pressures noticed by the engine when this is under high boost, make no mistake about it, the load will transfer very quickly from the factory alignment pins to the dowel pins that are right dead in the compression, or sorry, the combustion chamber, right where the cylinder pressure is the highest. So, and that in effect will prevent any cracking of the block happening either in the thick center in this area here, or the front plate or the rear plate. You don't see cracking going on in the middle because the center intermediate iron here is where the two pins join together, and they're submerged in quite a ways, and typically the load is just on the ends. So now we have much more support running those pins, and when we put our back plate down, we're going to find that it slips on very, very easy, and just by way of using the bearing as a guide, those dowel pins will sink into their respective bores, and the plate should just drop down, and that's what we're looking for, that type of accuracy. So we'll be accomplishing that here momentarily. And we already have our bearings and our gears pre-lubricated in this particular build, so we're not too worried about. And that's what we're looking for. Drops down into its exact location. Now what we need to do is we need to make sure that these extra long bolts that we are using from the Mazda RX-8, which are identified with these little counter bores in the heads, these extra long ones actually have to go through our dowel pins and into our new threaded holes, which is going to be that one, and that one. And those are going right through those pins that we put in, and clear through to the center thick iron. And again, it's being assembled more just like a 13B at this stage. And then as we move along, we'll be doing the exact same thing with the front ones. Be putting a little bit longer than stock tension bolts all the way through the front section of the motor, through the pins, all the way through the new dowel pins. And then we're going to be putting in the factory short tension bolts from the front. And again, the factory dowel pins with the cutback, and accomplishing exactly the same thing on the front as we are on the back, but we're going to allow the engine to have that bit of movement that we're looking for here. And we'll go through that again when we're putting this engine together, and we'll also remind people that this is a build video more at the request of the customer, because we offer that service where we will film your assembly. And thought viewers at home might be able to enjoy it also. And hopefully people will learn something. And just remember, this is a process that we've been using on 20Bs probably for about 15 years now. So it's been around for a while, proven to work. And we're just about done with this side, so we're going to get the engine turned over. One thing we're going to check real quick is our line board, just to make sure we have movement in the shaft, which we do, which is perfect. That's what we want, and we're going to flip it over and go the other direction now. So first things first with this, we'll zoom in on this housing a little bit here so you guys can see. We've already got the crankshaft keyway for the second member of the crank here. So we're going to flip this over and push that down. That's all it needs. Then what we're going to do is I'm going to get Mike to put a flywheel nut on the bottom of this and reach under and spin this lobe till it's either at 6 or 12 o'clock so I can assemble the other rotor easily. And while he's doing that, rotating everything around, I'm going to put the O-rings in this side of the housing, which were not in there when we first started because we needed to have it upside down on the engine stand, and we didn't want to run the risk of it falling out. So just going to put some Vaseline on the O-rings, get the O-rings in while Mike gets the flywheel nut on, and we will begin progress and get this engine front side buttoned up. So now that we have our O-rings in place and we have our journal at 12 o'clock, we'll go ahead and start doing the front of the motor. Again, this is a non-lap surface, but absolutely in immaculate condition. I mean, just beautiful. So again, you can see these are our 3 holes which we are going to use our dowels in. And just to remind you again, because this will all disappear as soon as we put the rotor housing on, you won't be able to see anymore. These pins, unlike the rear ones, are completely step down here. And that step will match this step and these pins, the factory pins, and we have movement in the front, which is what we want to accomplish. We want to be able to allow that front section of the motor to move around while we're adjusting our line bore and torquing the engine down, and throughout its heat cycle process, and when this engine learns, wants to find itself, when it wants to vibrate and flex and shuffle, it will have that factory availability to do so, and we won't be wiping out any center bearings or having any problems with destroying expensive crankshafts like the horror stories we hear about some of our people who call us in distress saying, what happened, I thought my motor was perfect, I've lost my motor. And yes, it does happen, and it happens more often than it should. And again, the main reason for that is they've gone and jacked with the factory line bore. They've either made it too rigid, or they've just said, you know, we don't care about this factory function. And I will add, there are some people that get lucky, and they for whatever reason, they have a line bore that's permissible that allows them to do what they're using the engine for. I mean, sometimes even in high horsepower racing, and they say, oh yeah, it works perfect, it's great. Good for them, and that's great, and if it works and there's no repercussions and no bearing damage, then who can complain? And who can really knock that person for continuing to risk it? But we found that when you do a strength mod like this on a top-notch, Class A, quality, high-level build that there is no need to try and cut corners or build shortcuts, and it's just plain and simple. Do it the right way, and as long as the customer is going to be happy with his horsepower, meeting his horsepower goals and achieving what he wants to achieve, that's what's important. So you'll notice that front section is loose because of these pins, because of the taper, and they will continue. It will continue to be loose. It's difficult for me to shake the housing enough for you guys to actually hear that that free play. But you see how nice everything slides in? I mean, it just drops right in. It's beautiful. Now I will say one thing, and again, this video is more intended for the owner. So he's going to be the first person to hear me say this, and I hope he won't be upset with me. But I will say, Colin, the owner of the engine in the car, he's gone a little bit balls out overboard on this build. He's a customer with the belief that everything should be done right, and he doesn't like shortcuts, and I agree with that. I will say that this engine, for what its purpose is, and I'm not going to tell people what he's using it for, because he may have some surprises in mind as to how he wants to present this car in this project, but it's going into an application that's going to use a turbo, of course, and he's going to be making some pretty big power numbers with that turbo. And whatever his goals are, whether they're pump gas or race gas or high boost or low boost, this engine is going to make far more power than it is designed to hold, than he'll ever use. So, you know, again, overbuild, underdrive, and you'll have the best results. In my personal opinion, I do not believe that this engine, for what its intended use is at this moment, needs things like the dowel pinning and the heavy-duty rotors. This is a serious build. This is a very, very strong, proven and tested design that we've used over the years. And for the application that I'm aware of that he's using it for, he simply does not require this, and probably won't if he leaves it designed for that intended use. I will say, though, if he ever decides to change his plan or decides to put on some big slicks, some big wheels and tires, some slicks on the rear of the car, and he wants to run race gas and crank the boost and run, you know, as much power as he possibly can, then this engine will be clearly designed to step up a few notches. So he's got he's got a lot of engine here for whatever future goals he decides to have. For the time being, he's just going to have one hell of an engine for the level that he's using the car. So we're going to button this up and put on the front housing. Again, this half bridge here is going to match the notch in this housing, and that's been consistent the whole way through. This is a beautifully ported piece, and yes, I did it myself, but apparently I'm attached to it, and I don't want to let it go. But I guess we're gonna put this on and close it up, and we will see if it'll hit those pins. And look at that, falls down and lines up, and it's the fit we were looking for. Absolutely bang on the money. So what we're going to do, put the big fatties in, one through the bottom dowel pin here, and then we got these two, which is going to be here and here. Those are our extra long custom ones that we actually made for this length. And then those 3 are factory. So we're just kind of mirror imaging what we did on the back side. Shut that off. So all in all, we couldn't be more pleased with how smooth this engine went together. And we've got our counterweights to install later, which are, you know, already corrected for balancing. We balance the entire rotating assembly on this motor. And all we're going to do tonight is finish off torquing this motor down and setting the line bore. So we're going to get some preliminary torque on all these bolts up here. And then we're actually going to loosen things back off and start cranking the motor around to set the line bore. And then we'll go through the torque sequence and we'll be done. So for starters, what we're going to do here is we're going to flip the engine over so we can get some of our long bolts in. And we don't have to turn the engine all the way up, we just have to tip it up enough to get the bolts up through the bottom. Thanks. That's one of the factory 12mm bolts that goes all the way through the assembly. That goes in about the, I'd say 7 o'clock spot. And then the one I just put in now kind of goes in between 12 and 1. This bolt that's going in right this second goes in exactly 12 o'clock. So there's not a lot of these to put in. So I'm just going to put the last few bolts in, and then while I'm doing this, I'll get Mike to put the to mock up the spacers for the front of the shaft, so we have the availability to torque down the front nut. And then we can also use the front of the crankshaft to rotate the motor over if need be. And for anyone who hasn't seen this before, we're going to use the factory designated 12mm bolts to start to slowly pull this engine together while Mike rotates the engine using the crankshaft nut, and at the same time he'll be putting some torque and some load on the crankshaft taper. And we're just going to slowly suck these together. We'll go through the first couple of stages just so we can show a little bit of this to people who haven't watched any of our other videos. It is very likely that we will not continue to film the entire torque assembly, only because it takes a little while and it's kind of boring. And I think our owner of this engine is likely going to want to focus more on his assembly of the stuff behind the front cover and his very custom oil pan that we had built for him, which is really cool. So probably what we're going to do is cut it short here, and just to finish off, as Mike's rotating this around and we've got some preliminary torque on our factory 12mm bolts, which what we've used to more or less pull the engine together so we can set the line bore as accurately as we can without going through the entire torque process. we're there now just from the feel that I have for the amount of pressure that's actually been put on these bolts, and how far torqued they actually are. We're there. So all we're going to do now is we're going to just we're going to loosen this off, and we're going to just make sure that we actually have a crankshaft that will there we go, that will actually hop up and down and present a line bore. And this is what we're going to check the line bore. Very simply, we have a rigid semi-torqued crankshaft assembly, and we're just going to put our pry bar underneath and lift up and watch it fall back down under its own weight. Up, down, so on. Okay, and that's a good sign that our line bore is getting close. So again, we're probably not going to take this through the entire procedure on camera because it takes a while. But rest assured, everything's going smooth so far, and we're going to continue to snug up our large 21 mil tension bolts, and then we're going to work our way through the 10 mil bolts, and we will bring you guys back in approximately when our engine is dressed with front cover and everything behind the front cover, and custom oil pan and motor mounts and maybe clutch and flywheel, and show you this engine complete, ready for installation in Colin's car. So when we saw you last, we were in the engine room putting together this half Bridgeport 20B. The car it's going into is a first generation RX-7, which is the car behind me. We've got the engine partially dressed and put on our custom front engine bracket that we fabricated, and we have a corresponding custom brace that we built for the car, which we'll show you when the car is down, and just walk you around the engine once, and then we're going to put it on the engine crane and install it in the car. This car actually just had a twin disc clutch and chromoly flywheel attached to the counterweight before we put this T2 transmission in. We've also got a custom rear cross member here on the transmission that we modified for this car, whereby we have some polyurethane bushings and some extensions, so we could actually slide the whole transmission and engine assembly back to make room for the longer 3-rotor engine. And another thing we've done is we've done a custom shifter housing on this transmission, where we've actually taken the shifter housing from back here where it belongs, and we've moved it forward by shortening the body, the tube that the shift rod goes through, and actually having the rod shortened. And we had them EDM a new roll pin hole, so we could actually take this whole assembly and move it forward 100 millimeters. And that was done obviously to make so the factory shifter lines up with the hole in the floor, so we don't have to have a shifter that's relocated way far back. So I guess here we go. We're going to hook it up to the engine crane and get it put in the engine bay. So last you guys saw was us using the engine crane and putting the Bridgeport 20B engine into this chassis. We didn't go into too much detail about telling you about this car, but this is a 1979 first year made RX-7. A few of the things we did to this car to accommodate a little bit more strength and to handle the extra power is we went with the larger 14-inch GSL-SE wheels. Now, these wheels and tires are not going to be near enough to hold the power this car is going to put down. But we did have a request from the customer to basically make this car a sleeper, and wants the appearance of a stock vehicle. So the 14-inch wheels and tires were about as big as we could go. We've got the brand new calipers with stain the braided hoses on the
the front. And then moving back, you can see we did the same thing on the rear. We put the large GSL-SE back rotors with new calipers and stainless braided lines on the back as well. And then instead of changing the entire differential assembly and rear end over, what we did was we stuck with the 1985 rear disc brake diff housing. And we actually installed a CAS differential into the diff housing, put a larger drive shaft flange on so we could put on the large greasable U-joints, and we then customized the drive shaft to go to the Turbo 2 transmission that this engine is coupled to. We did have to modify the cross member on the transmission. This is actually a Series 5 transmission which has been modified, and the brackets have been brought back to allow this transmission to come further back, because we don't have the room when you have such a large, long engine assembly. So not sure if you can see up through the floor there where the shifter goes, but we did have to cut the floor back a little bit. But the good news is the shifter actually still lines up with the hole in the floor. Okay. Now the challenging part about this was, aside from the fact that we had to make these custom cross members to mount this engine assembly in the car, which is what we're looking at now. This is the lower one, and it's a piece that we built and then had powder coated. We used some FD engine mounts in the middle, and then we went ahead and made a cross member on the front of the engine to couple the two custom cross members together. The next thing you're looking at here is the custom oil pan, which is based off of a factory 20B pan. We maintained the level sensor on the rear half. We did have to do a channel in the inside of the pan here in order for this steering arm to go through, and then we built a custom large sump here to hold a little extra oil and to compensate for the fact that we removed some material here for this steering rod. And then if you notice, the front little sump of the factory 20B pan, which is more a clearance sump for the factory pickup, actually blends in with this factory cross member beautifully. So the whole thing dropped in, and you know, this is again based on a lot of measurements and engineering that we did to make sure that everything sort of fit tight together. We have very, very minimal clearance between the bottom of the engine and this cross member. But that's all we need. It's enough. It's a tight fit, but we made it work. And this is something that was probably the most challenging part of this project. This is the front of the car with the factory grille on. I'm not sure how well you can see this here, but we did put a second gen oil cooler on the bottom here with some Earl's fittings and stainless braided hose. Then we've got our custom aluminum radiator in here with an electric fan pushing through from the front. And then we've got our custom intercooler in here that spans all the way from left to right. It's a very thick, 4-inch thick intercooler. So that's sort of what you get by looking at the front of the car. So now we're actually sitting inside the car. You can see here there's some gauges mounted in the dash here. There's a wideband and a boost gauge here that we still have to mount. We don't have the shift boot in, but as you can see, our shifter is lining up right in the general area of where the factory shifter sat. If I turn around here and bring you to the back, we've got the rear panels off at the moment. What we've used here is a twin pump surge tank, and we have two Walbro 430 pumps inside this surge tank. Underneath the car we actually have an aeromotive transfer pump that transfers fuel from the factory tank into the surge tank, and then what we have is the twin pumps feeding out of a number 8 fuel line, and then of course we run that line through bulkhead fittings, through the floor, and then underneath the car up to the engine bay. And here's the moment you guys have been waiting for. This is our 20B engine in the engine bay. This engine runs, and you can see it's a tight squeeze, but we do have clearance on everything. Main drive pulley, water pump pulley, even the air filter has about a ½ centimeter of space up to the radiator. Again, all the things underneath the hood here have been customized for this project. All the throttle body elbow and the piping, and the fuel system components, dry cell battery, 6 high energy XL coils mounted on a custom coil bracket, some MSD wires that we built for the ignition. We've got our gauge adapter underneath the oil pedestal to do our oil temp and oil pressure gauges. There's our fuel pressure regulator with the fuel pressure gauge on the front. And again, not sure if you can see our custom cross member down there, but it was very challenging to get this engine in the car to the point where the hood would close and make sure that the shifter lined up with the hole in the floor and that we had enough clearance to put our heat exchangers up front and maintain even our factory cowling for the top of the radiator to the front of the hood. There's our turbo system, which we built from scratch, not the turbocharger, of course, a Borg-Warner turbo, but we did use our 3-rotor manifold jig that we used to build our FD manifolds as the basis and the platform to design this manifold, and we actually made the improvements to the jig so we could build the manifold for this car. Once we had the manifold built and powder coated, we put our wastegate dump and custom 3.5-inch downpipe, which we fabricated off the same jig, and basically tried to produce everything so we had ample clearance without compromising any quality or any flow. And I will now show you that in fact the hood does close. So now the fun part. We're going to start the car. Let's fire it up. Idle, which is about 1600 RPM, 1540 right now. This car does not have a final exhaust system on it. It's a very temporary exhaust. The 3.5-inch stainless downpipe, of course, is staying, along with this wastegate front section is final, but the back section of the exhaust is not final. There's a small exhaust leak that you're hearing as well, but